we're going to extend our knowledge of friction and apply the concept of friction to wedges and frictional belts, flat belts, where friction is the way that torque is generated about a pulley. Now, as the belt wraps around the pulley, the tension actually changes because of frictional forces along the entire length of the contact between the belt and the pulley. So you're going to see how to determine the forces on a wedge and also how to relate the tension on two sides of a belt across a pulley. Now, there are other things in the slides you should go through, but primarily we're going to talk about analysis of the wedge, how do we do that, and then analysis of a belt. Both are pretty straightforward and involve friction, so this should be an enjoyable lecture. What applications are there for this? Well, wedges are often used to hold things in place. Airplanes commonly use wedges. Cars, you might chock the wheels, right? You might wedge the wheels before you work on the car to make sure the car doesn't move. Or this large piece of pipe, which is very heavy, could be wedged so that it doesn't move. Well, you don't want that wedge to just shoot out, right, or slide out. You want the wedge to hold it in place. So how is it that we could analyze this wedge and make sure it'll work? For example, what angle should that wedge be? Well, we could try a couple different angles, analyze them with statics, and determine whether that pipe would be able to just push the wedge out, or given a friction coefficient between what looks like to be a wood wedge and the steel, the rusty steel, we could calculate, at a decent angle or a minimum angle so that the wedge stays in place and the pipe doesn't just roll and push the wedge out of the way. So how would we determine the amount of force required to pull it out? Because if you think about it, if we have to apply force to pull this thing out, that means the wedge is self-locking. That's what we want for a pipe like this. I don't know about you, but I don't want to have my back to this, looks like about an inch thick or more steel pipe, and it come rolling towards me, something like Indiana Jones with that stone rolling toward him. I want to avoid that. I want the wedge to work. I also don't want my car to roll if I've chalked the wheels. So how do we determine that? Well, another application for this concept, it's interesting these two things are closely related, wedges and belts, but another way that we can apply these concepts of friction is to a belt drive. If you take my class Machine Elements, I'll teach you about sizing a drive like this and how you select the proper size of belt given the amount of power that needs to be transferred from the motor to whatever this driven machine is. It looks like maybe it's some type of a compressor or something. Anyway, so when we have a machine set up like this, one of the reasons for using a belt, by the way, is the belt is somewhat forgiving. If the machine chokes or locks up where it can't turn, the belt can actually slip, and that doesn't damage the motor as badly if it's not noticed immediately. If you have a motor and the rotor is locked and it can't turn, you're applying current to that motor, the motor will burn out pretty quickly because all the energy goes into the motor and just turns into heat rather than into mechanical work. And so it overheats the motor. Anyway, so how do we deal with a belt like this? Because you might think, well, so far we've learned about pulleys in this class, and when there's no torque on the pulley, well, then the tension on either side of the rope or belt or whatever it is the same. That's true, but when there's torque being applied, because that's really what this motor does, it applies torque through rotation, and then the driven machine requires that torque through rotation, then there is a difference. There has to be a difference in the tension on the two sides of the belt. Now, when you install the belt and the machine's not turning, the tension on both sides of the belt is the same because the motor's able to just, spin freely. But when you turn on power to the motor and it's actually transferring power to the driven machine, then there's a so-called slack side and tight side. What happens is as the motor turns, let's pretend this motor is turning, say, clockwise, the tight side will be the top side, and then the slack side will be the lower side of the belt. And it's that difference in tension that actually drives the pulley, the output pulley that's driving the machine. And so how do we deal with it? How could it be that there is a difference in tension between these two? Well, we'll see that, but it's absolutely necessary in order to provide a torque to transmit power through to the machine and keep it rotating, say, at a constant speed. Statics can be used for analyzing that situation because the output wheel and the motor and all this are turning at a constant speed. There's no acceleration once we get up to speed, of course. And so the analysis we're about to perform here actually is used in my Machine Elements course because it's absolutely necessary. So anyway, how can we decide if the belt will function properly without slipping? Well, it turns out that the tension in the belt is a really important parameter. A very small belt can only take so much tension. If you calculate that you need a huge tension, you're going to need a bigger belt. It's pretty simple. So there's got to be a Jaws joke in there. We need a bigger boat, but I don't know where it's at. You make it up. So anyway, we're going to analyze this situation as well as wedges. Another application also in my machine elements class is a so-called band brake. So you apply a force P to the lever. You notice that point C moves to the right, point A moves up. Both of those tend to tighten the band brake, and you don't usually have a long throw, a long distance of motion to engage the brake. But anyway, so how do you analyze this situation to determine, for example, how much force P has to be applied? And by the way, if there's so much tension in the belt, or band, really we would call it, how do those two tension forces relate to one another? Because the tension applied to A will be different than the tension applied to C, since there's rotation of the wheel and power being dissipated via friction. Anyway, so we'll learn about this. This is just another application of the same idea that we were talking about with belts a moment ago. Now, to analyze a wedge, what do we do? Well, what is a wedge? It's a simple machine where a relatively small force is used to lift a large weight or to prevent that weight from rolling back, for example. So if we think of a wedge, then what we need to do in order to analyze it is to draw a free body diagram of the wedge so we can understand what's going on. So here's a typical wedge. Now you notice this wedge is being pushed into and under the weight being lifted. How do I know? Because the friction force is acting opposite, right? The friction force is trying to keep the wedge from going in, but we're applying a pushing force P to force the wedge under the weight and thereby lift the weight a bit. So we started with that. Notice that the friction forces are always in a direction opposing motion. Okay, so in this case, we know we're trying to put the wedge under the weight because the friction forces are going in the opposite direction. And of course, we know we're applying force P, so we're trying to push it under the weight. Those friction forces always act along the contact surfaces, so they're not just opposite of P. In this case, it looks like F1 is opposite of P, but F2 has some angle theta with respect to horizontal. So there's a vertical and horizontal component of F2, and then the normal forces are just perpendicular to the two contact surfaces. So N1, for example, in this particular case, looks like it's completely vertical, whereas N2 has a negative X component, if we assume that going to the left is a negative direction, but it also has a significant downward component as well. So what do we do after making the free body diagram of the wedge? Well, next we make a free body diagram of the thing on top of the wedge, or the thing that's being pushed by the wedge. Now that can be more than one thing. We could have two things we're separating with a wedge, and so we need a free body diagram for both of those bodies. In the case of ground, we don't really need a free body diagram for ground because we just have equal and opposite normal and friction forces on the ground. So we need to write down or clearly distinguish all of the other forces acting on the body besides the forces from the wedge. Now notice it's important to realize that the forces applied to the bottom of the weight are going to be equal and opposite to those on the wedge. So this doesn't add two more unknowns. All it does is represent the same unknowns in another free body diagram. So it's the communication between the wedge and the body, at least mathematically. And then after that, all we have to do is apply the equations of equilibrium both to the body being lifted and to the wedge. Now the equations we have are the sum of forces in X and Y, and then also we'll have to use a frictional equation, so impending motion friction equation. Because think about it, if we're trying to slide the wedge in, then we're on the edge, where we're maximizing the friction if we're about to have motion, and the whole point of a wedge is to have motion. So which free body diagram should we start with? We've got two. Most of the time, what you'll find is that analyzing the free body diagram of the body and not the wedge is more beneficial. It's not always the case, but if you're at a loss where to start there, because a lot of times you know weight or some external force being applied to that body, and you'll be able to sum forces well enough to figure out what's going on with the friction and then back that out to the wedge. But that's not always the case. What you really want to do is just analyze the free body diagram where the number of unknowns is less than or equal to the number of equations of equilibrium and frictional equations that you have. That's really what you do, but it just turns out a lot of time it's the body, not the wedge, where you have enough information to solve it. And then you take, for example, in this case, F2 and N2, move them over to the wedge, and then you have enough to solve the wedge as well. And that's not always the case, like I said, but it's possible. Now, what about if the wedge is about to slide out? So if it's being lowered, this is what I was talking about with that pipe, we most of the time want wedges to be self-locking. We don't want them to just squish out on their own. It's kind of self-defeating. So we want the wedge to be self-locking. What that really means is that there must be some positive force required to pull the wedge out from underneath the weight, and friction acts in the opposite direction. So basically, without any pulling force, the wedge does not come out on its own. So if we continue then into belt analysis, if you think about a flat belt passing over a pulley, you could break up that belt into little bitty segments along the length of the pulley, and there is friction acting between the pulley and the belt. Otherwise, no torque could be transferred from the belt to the pulley. There must be some force acting at a radial distance from the center of rotation of the pulley in order for there to be a net torque on the pulley. And of course, for a motor to do its job and transmit torque to an output machine, both the pulley on the motor and the pulley on the machine must have some friction in the belt. Otherwise, the belt would simply slip over the smooth surface, right? So we're going to assume that a flat belt, passes over a curved surface with a contact angle equal to beta radians. Now, beta is an angle, but it's measured in radians. It's really important because the equation we use for this absolutely requires radians. If you've got your calculator set in degrees, you need to pause the video right now, go and learn how to set your calculator into radians mode. Hopefully you already know that. If not, pause the video, go figure it out now. And I'm sure you can find a tutorial on YouTube or wherever to tell you how to do that if necessary. Now, if we're at the point where the belt slips or is just about to slip, then the tension T2 must be larger than T1, because think about it, friction, we're pulling it right that way with our hand, for example. The friction is acting in the opposite direction, okay, because it's trying to resist that motion. Now, the way you come up with this equation, T2 equals T1 times E to the mu beta, the way you come up with that equation is by taking a differential length of the belt around the wrap angle and integrating. I'm not going to show you that here because I really don't believe that derivation of an equation really helps you a lot. I think seeing how to use that equation helps. And then what I've found is if I go back to the derivation afterwards, it actually makes more sense once I understand the result. So I'll leave it to you how you do that. You can go back to your textbook, look at the derivation now if you want, or look at it later. Here's the point. Couple things. T2 is always greater than T1. So you need to find this equation in your book. I don't remember the page number right now, but find it. Make yourself a note that T2 should always be greater than T1, okay? Then E is the special number, 2.7 whatever, Euler's number. It's on your calculator somewhere. I don't know where it's at. You need to go figure that out also. And sometimes it's EXP, the exponential function. If you're using Excel, it's definitely EXP. It's a function in Excel. Mu is the friction coefficient, same kind of friction coefficient that we've had before, right? We had a kinetic friction coefficient and a static coefficient, friction coefficient. Which one is this? It's the static, because we're assuming there's no slippage. We might be at the limit of slipping, but we're assuming there's no slippage. And then beta, of course, is the wrap angle, again, measured in radians. So make sure you know how to set your calculator in radians. Make sure you've written down that T2 is greater than T1, and make sure you know how to use the exponential function, because mu beta is multiplied together and then becomes the exponent for E in this equation.